Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I'm studying in CSC AI and ML, that is Computer Science and Engineering, with the specification of Artificial Intelligence and Machine Learning, 4th semester, Institute of Aeronautical Engineering. In this video of the complex engineering problem of the subject of design and analysis of algorithms, the topic I'm going to discuss about is the necklace problem. So let's dive into the video. So first of all, let's go through the contents. In the first place, I'm going to explain the necklace problem and its graph theoretic foundation. I'm going to introduce it to you. And the next, the formal problem statement, the graph modeling, and the conditions for a valid solution, which all of them make a problem formulation. I'm going to explain about that. And the next, the Hire-Holzer's algorithm with a Python implementation and sample output, the algorithm and implementation. I'm going to explain about that. And finally, I'm going to conclude the topic with the key takeaways and broader engineering relevance. So first of all, the necklace problem is a classical combinatorial challenge in algorithm design. Given a set of beads, each with two colored ends, the goal is to arrange them into a closed loop such that adjacent beads share matching colors. Here the graph transformation. The colors are vertices. Each distinct color becomes a node in the graph. The beads are edges. The, each bead becomes an edge connecting its two color nodes. The core insight here is to arrange all beads in a closed necklace. Arranging all beads in a closed necklace is equivalent to finding an Eulerian cycle, a cycle that traverses each and every edge exactly once. This transformation unlocks powerful graph theoretic algorithms to solve the problem efficiently. So this was all about the introduction to the topic. Now let's go through the problem formulation. The problem statement here is that given a set of beads, each with two colors, we have to determine whether a valid closed necklace can be formed, and if so, we have to construct the arrangement. Here we have two requirements. First requirement is that all of the vertices must have an even degree. That is, all of the vertices must have only two or four even number of edges, and every node. This means that every node appears even number of times. Every color appears even number of times across all beads. The second requirement is that the graph must be connected, as we all know that the necklace is always connected, and the arrangement of all of the color nodes used by beads must be as per the algorithm. Here the conditions for a valid necklace are the time complexity. Hire-Holzer's algorithm runs in big O of E, linear in the number of beads, making it highly efficient for large inputs. Here, even degree, each and every vertex must have an even degree, and the entire graph must be connected. It's a necklace, of course. All the beads must be connected, as we all know. Hence, this is the problem formulation. Now let's go through the algorithm and implementation. Here, algorithm goes through four stages mainly. First, it starts and it traverses through all the nodes. Whenever the condition gets dissatisfied, it backtracks, and through all of this process gets completed. This algorithm greedily traverses the graph, removing used edges to avoid repetition, then splices partial doors into single closed cycle. What does this Python implementation do? First of all, this program checks whether the necklace can be formed using beads, and if possible, it returns the arrangement. It is based on the concept of Eulerian cycle, as we all know. Here each bead is equal to connection between two colors. We must form a loop using all beads exactly once. Here the import statement. From collections, import default dict. Here the default dict list automatically creates empty lists for new keys. It is useful for building graphs clearly. Here the here the function is defined as find underscore necklace with an attribute of beads. Here beads is a list of pairs. Pairs means edges. Each pair represents a connection between two colors. And construction of a graph. Here the graph is equal to default dict list, and for u and v in beads, graph u dot append v, graph v dot append u. That means here it converts the beads into an undirected graph. Each color is vertex, each bead is an edge. For example, beads is equal to red, blue, blue, green, green, red. That is the ideal one, perhaps. Here the graph becomes red, blue, blue, green, green, red. That means red color node, red bead connects to blue, blue node, blue bead connects to green node, green bead connects to red node. Here the for loop for vertex in graph, if length of graph vertex is not even, we have to return no necklace possible. That's what the code is saying. Here an important rule to note is to check Eulerian condition is that for every necklace, that means for every Eulerian cycle, every vertex must have an even degree. Degree is equal to number of connections, as we all know. If any vertex has odd degree, necklace can't be formed. Here initialization of stack and path. Stack is equal to next iter graph, path is an empty list. By starting from any vertex, stack is used for traversal and path stores the final answer. That's what the initialization telling. And here the main algorithm, the while loop, which you can see there, it is the core logic while stack. This is based on Heyerholzer's algorithm for finding Eulerian cycle. Step 1. By taking current node, v is equal to stack of -1. Here if we look at the top of the stack, it looks like the top of the stack. Step 2. If edges exist, that means if graph v, if current node still has neighbors, u is equal to graph v dot pop graph u dot remove v. What happens here is that by removing the edge vu, it also removes the reverse edge uv. This ensures that each bead is used only once. It removes duplicates basically. Stack dot append u. Here it moves to the next side, next node. Step 3. If no edges are left, that means else path dot append stack dot pop, that is the dead end which is reached. The node is added to the path and backtracking happens here. And finally return path colon -1. This is the return statement to return the final path. Here it reverses the path to get the correct order. Let's go through an example execution. Beads are red, blue, blue, green, green, red. Let's go through the step-by-step execution of this. All vertices have a degree 2 or even degree. Eulerian cycle exists. Output here is red, blue, green, red. This forms a closed necklace. Key concepts here. It converts the problem into graph theory problem. It uses Eulerian cycle condition, all even degrees. It uses Hierholz's algorithm. Stack is used for backtracking. Each edge is used exactly once. The time complexity here is big O of E. Traversal is big O of E. Overall, the time complexity is big O of E. Here E means number of edges. That means it is efficient. Therefore, the overall summary for this is that this code if checks if a necklace can be formed by verifying Eulerian cycle conditions. Hence, this is all about the algorithm and implementation. Now, let's finally conclude the topic. The necklace problem elegantly demonstrates how a real-world design challenge can be abstracted into graph theory and solved with a provably efficient algorithm. Here, I would like to give three takeaways. First is that mapping color to vertices and beads to edges reduces the problem to finding an Eulerian cycle, and a valid necklace exists only if all vertex edges are even and the graph is connected. The efficient solution is that the Hierholz's algorithm constructs the necklace in big O of E linear time. It is suitable for large scale inputs. Hence, the necklace problem is a very important problem and it is a very useful problem in design and analysis of algorithms. Hence, this is the final conclusion of the topic. And finally, I would like to sincerely thank all of the respected professors for giving me this wonderful opportunity to talk upon this wonderful topic. Thank you.